Okay, so welcome all to today's for CNRE's seminar series. Today's speaker is my great pleasure to introduce Professor Sareen, who's today's seminar speaker. Professor Sareen is an assistant professor in the Navy Department, also has an appointment in mechanical engineering, and she's joined the department since Jan of 2023. Before which she was a postdoctoral fellow at the University of Minnesota in the Aerospace Engineering Department, where we overlapped actually before there. So Professor Sareen obtained her PhD from Monash University in Australia, her master's from École Polytechnique in France, and her work has won awards like the Best Thesis Award and Outstanding Research Paper Award at the Australasian Fluid Dynamics Conference. And here she heads the Experimental Fluid Dynamics Lab, where she works on bio-inspired flow control and FSI with emphasis on energy. And today she's going to talk to us about a pretty interesting idea on using morphable skin for adaptive flow control.
All right, thank you, Mahesh, and thank you everyone for being here. So today I will talk about adaptive flow control using smart morphable skin. But before I proceed, I would like to acknowledge that all the research work that I'm going to present today was performed by Rodrigo and Nanda. So Nanda is a graduate student in my lab, he's here. And Rodrigo was a postdoc in my lab and recently been supported by CNRE. And other students, Aditya was an undergrad student who did 490 in my lab. He contributed in the initial phases of the project. And also Parth who's a Navy master's student, was involved in the initial conceptualization efforts in project 2. All right, so when we talk about adaptive surface morphing, it's very prevalent in nature. Right? So over billions of years of evolution, these natural creatures have evolved very fascinating ways of adaptively morphing their surface topology or shape in response to external stimuli. And this is one example here of puffer fish. So in presence of a predator, this puffer fish puffs up or inflates its entire body and actuates these really sharp spikes, which gives the puffer fish survival advantage. On the right, we're looking at falcon bird, which morphs its wing when diving, and that allows it to reach whooping 240 miles an hour of speed. So we see through these examples that adaptive morphing in nature provides advantages in survivability, hydrodynamic or aerodynamic efficiency, and maneuverability. And these are just a few examples that we see in nature. And one particular example, which I find really fascinating, is that of a short fin mako shark. So they are the fastest shark in the world, and they're also called cheetahs of the ocean. And they can reach top speeds of 62 miles an hour underwater. And of course, they have very powerful muscle and very streamlined body. But one of the key reasons scientists believe for their efficiency is these very small, tiny scales called dermal denticles, which are spread on the entire body. And they act as riblet. And then it's a very well-studied problem, and riblets can reduce frictional drag by as much as 10%. But you might be wondering, where is adaptive surface morphing in this case? So interestingly, in 2012, Professor Amy Lang's group at University of Alabama, in collaboration with their evolutionary biologists, collaborator at University of Southern Florida, what they found was when the shark takes sharp turns or when it undulates to maneuver at very high speeds, the flow separates at these highlighted regions on the side of the flank and also at the trailing edge of the caudal fin. And what they found was that the shark scale in those regions, they bristle. So they lift up and bristle whenever they encounter flow separation. And this happens at an order of milliseconds. And it's beautifully shown here in the schematic, which I took from the report. So when the flow is attached, they are perfectly streamlined and they act as riblets. But when we have flow separation, they lift up passively. So this is a passive mechanism. They don't use any muscles for this. And then they inhibit the flow separation and thus reduce pressure drag. So as you all might know, at least fluid dynamicists here would know that flow separation is really detrimental, right, for the efficiency of swimming and leads to pressure drag. And this is a mechanism by which these sharks, they can adaptively change their surface texture to avoid or inhibit that flow separation that reduces pressure drag. And in fact, this passive bristling reduces pressure drag, much like dimples on a golf ball. So if you look at a golf ball, so if you have a sphere and you add dimples on it, it can go as much as 30% farther compared to a smooth ball. So when we look at sphere, it's a bluff body. So the flow is massively separated. You have this flow separation because of the adverse pressure gradient, and you have this wake behind it. And that's the leading cause of the pressure drag, right? And when we add these dimples, then what happens is that laminar boundary layer that develops on the surface of the sphere gets transitioned into turbulent boundary layer. Now with increased wall momentum, it can resist the adverse pressure gradient and separates at a later location. And that happens everywhere. And then in effect, we have very thin wake or narrow wake at the back of the golf ball, and that leads to a dramatic reduction in drag coefficient. So if you look at this chart, which represents drag coefficient as a function of Reynolds number, so this is taken from Choi et al. From Annual Review of Fluid Mechanics. So if I take your attention to the smooth curve, which are these solid gray symbols here, so they represents drag of a smooth sphere. And they are represented here from the seminal work of Achenbach. So you see that in the subcritical regime, the drag coefficient is almost constant. It hovers from 0.5 to 0.55. And when the Reynolds number goes beyond a critical Reynolds number, the laminar boundary layer transitions to turbulent boundary layer, and we have this rapid decrease in the drag, which is also known as drag crisis. And then if you keep increasing Reynolds number, the drag starts rising again. And now, if you add dimples, so if we look at these light blue color cross symbols, which are the results from Choi et al. From 2006, we see that with dimples, we can reduce drag much earlier. So now we can have that drag crisis at a much lower Reynolds number. We see this dramatic drop, and then the drag constant is almost, it plateaus. But if you continue to increase Reynolds number, you can see here, we don't have data yet, that the drag would be much higher than the smooth, right? And then if you look closely now at the solid square blue symbols here, and these are results from Behrman and Harvey, with much higher dimple depth ratio, where K is the dimple depth and D is the diameter of the sphere. So it's much higher dimple depth ratio. We see that now we can reduce drag at much lower Reynolds number. But if you increase the drag coefficient in the post-critical regime, it's actually higher than the shallower dimple. So this tells us something. What it tells us is that there is no one size fits all. So if your goal is to minimize drag across a wide range of varying Reynolds number, we need deeper dimples at lower Reynolds number. And as we increase the Reynolds number, we need to get shallower and shallower dimples, eventually reaching a smooth configuration. But you can see here that we have only 2 data sets here, and the dimple depth ratio and the coverage ratio in those 2 studies, they were matched with professional golf ball. So we don't have any systematic study reporting the effect of dimple depth ratio. So we need a strategy by which we can change the dimple depth here on demand or adaptively that allow us to minimize drag across a varying range of Reynolds number. So that brings us to the research question to address. So can we develop a strategy to minimize drag on a sphere over a varying range of Reynolds number? And if you're wondering why we're interested in sphere, then it's the most basic prototype of 3D vortex shedding. And it has adverse pressure gradient, you have massive flow separation. And this is one of the prototypes that you see that in academic community, they use that for most of the fundamental studies. So we will look at sphere and see if we can develop a strategy by which we can change the dimple depth on demand or adaptively with flow velocity. So when I was thinking about this idea at MHL, you might have also noticed there was a NEEX project going on, advised by Professor Mackey, where they were looking at ice breaking. And you would see those pickleballs that they were using as a surrogate for floating ice everywhere in the towing tank and also in the wind wave tank. So during that time, when I was looking at those pickleballs everywhere at MHL, an idea struck my mind. So I literally took one of those pickleballs, so don't tell Nick's team here or Professor Mackey, and I went to the dollar store and bought a balloon, literally a balloon, a syringe, and a tubing. So what I did, I took the pickleball and covered it with the smooth balloon and used the syringe to suck the air out of that pickleball. And as you would have guessed already, that actuated dimples, right? And what I saw was when you change the pressurization levels, if you take more air out, you can get deeper dimples. So that means by changing the depressurization levels, we can change the dimple depth on demand. And coincidentally, during that time, I had an undergrad student from ME320 and NE320 that I teach, who came to my office saying that he's really interested in studying aerodynamics of golf ball. So I literally showed him the toy model that I developed. And I said, let's make a precision pneumatic actuation system here that would allow us, based on this, change the dimple depth on demand precisely by doing depressurization. And that's what he did. So he 3D printed rigid skeleton. So these are the 3D printed rigid skeleton, and it has holes spread across the entire surface area. And they were 3D printed here at Fabrication Studio. And then we took a thin latex membrane of thickness 0.276 millimeters and shear modulus of 340 kilopascals. And we wrapped it around. So the preliminary actuation system, we just had vacuum pump to suck the air out. And we had a regulator by which we can manually control the depressurization level. And we had pressure gauge to see what the depressurization levels were. But as we discussed earlier, here our goal is to actually change and program that dimple depth such that it can change with the flow velocity. And for that, we need a mechanism by which we can program. So that's when the postdoc, he added Arduino and solenoid valve, and then we can program it Arduino and control it through the computer. And that allowed us to change the dimple depth on demand. So here, what we are seeing is as you increase the depressurization levels, the dimple depth increases. And then in the video on the right, you're seeing that when we increase the depressurization, there were dimples, deeper dimples, and then we released the vacuum pressure, it reverts back to the smooth configuration. And this might look, in theory, really easy to fabricate, but this actually requires a lot of meticulous attention to detail and precision in hand. And that's where Nanda came in, and then he fabricated these models. Okay, so now we wanted to calibrate this so that we can relate how we can change the dimple depth precisely with the pump activation time here, which is for how long the vacuum pump is on. So we used 3D laser scanner with a resolution of 5 micron from Professor Steve's lab. And then we have now the calibration. And then by setting the pump actuation time, we can precisely control dimple depth. And then here, the precision that we could achieve in dimple depth was 0.01 millimeters. So once we had our morphable sphere version 1.0, there will be several versions throughout the talk. We were ready to test it. So grateful to the University of Michigan Aerospace Engineering Department who gave us access to the wind tunnel. So we tested this morphable sphere and 2 feet by 2 feet subsonic wind tunnel at GFL Labs, where the flow speeds could be varied from 5 meters per second to 22 meters per second. So that gave us Reynolds number varying from 60,000 to 130,000. It's not as big as we would like, but that's the experimental limitation that we had. And then we varied this dimple diameter ratio from 0.01 in increments of 0.001. And we kept the dimple diameter ratio, so the diameter of the dimple to the diameter of the sphere fixed, and we matched it with Choi et al. 2006, which is also matched with the real golf ball. And the dimple area coverage ratio in this case was 55.6%. And we did simultaneous force measurement and near wake measurements. We employed 2D particle image velocimetry, and we were looking at an equatorial plane, which was passing through the center of the sphere. So first, we did validation experiments where we compare our results with the benchmark results to make sure the setup and everything is validated. So first, we are looking at, so in the CD versus RE chart, again, these solid gray symbols, they are the benchmark results from Achenbach. So first we do is a smooth sphere, which is rigid. So it's literally a smooth sphere, not the morphable sphere, which is the circular blue symbols here. And then we also employed our morphable sphere version 1.0 in the smooth configuration where there is no dimple depth actuated. And we can see here that the rigid counterpart and the morphable sphere in the smooth configuration, they match pretty well. And they also match pretty well with the seminal work of Achenbach, and the slight variation are within the margins of error. So that was good. The setup is validated, but we also want to validate the morphing strategy, right? That we can attain a fixed dimple depth on demand and stay there for as long as we like. So in order to test that, we 3D printed, again, a rigid dimpled sphere. Here we matched the dimple depth ratio with that of Choi's. So Choi's results are in this square gray symbols, and the rigid dimpled sphere that we had is in sand color. And then we again actuated this dimple depth ratio with the morphable sphere, and that is shown in the triangular symbols. So first thing to note here is that the morphable sphere and the rigid counterpart, they match pretty well, right? And if we compare that with that of Choi et al., we see that there's slightly higher drag compared to what they had. And that is what we believe is because the area coverage ratio in our case is 55.6% compared to 73.6% in Choi et al. And then there was a preliminary study by Oki et al. In 2012, where they looked at the effective coverage ratio. And as you increase the coverage ratio, what they found in their preliminary results was that you reduce more drag. So we believe it comes because of that. And we couldn't match the coverage ratio exactly with them because it compromised the structural integrity of the core that we had, because it's 3D printed, we have several holes, and that very high coverage ratio compromised the structural integrity. So we had to go for a lower coverage ratio. So until now, everything looks good. We have a morphable sphere. We can get a very good, precise control over dimple depth. It matches pretty well with the prior studies, and we can attain a fixed dimple depth on demand and we can stay there and the results match with the rigid counterparts. So now we were ready to do the systematic study on effect of dimple depth ratio. So here, we're looking at CD as a function of RE. If we look at K by D 0, which are these symbols here, so we see that in this subcritical range that we were testing it hovers around 0.55 and it's constant. And as you increase the dimple depth ratio in the direction of the arrow, we see that as we were expecting from prior results, that we will see the rapid drop in the drag coefficient and the critical Reynolds number, where you start seeing that rapid drop, it decreases with increase in dimple depth ratio. Another thing to note here is that if you continue to increase K by D, so we have that plotted on a separate figure so that it's not very messy. So this is K by D of 0.006, and on the right, we are looking at all the K by Ds which are higher than that. And we see that in the post-critical regime, the drag coefficient is actually higher than what you get at lower K by Ds. But now we have this systematic variation, and we can think about doing adaptive control. But before that, it makes sense to have fixed RE to simplify things, fixed RE, and then we change the dimple depth ratio and see what happens. So looking at only two Reynolds numbers here, 90,000 and 120,000. So what we see here is if you keep the Reynolds number fixed and you increase the dimple depth ratio, we see a dramatic drop in CD. And then we have this optimal dimple depth ratio where we see minimum drag coefficient. And if you keep increasing, the drag actually starts increasing, right? And that's what we saw for every other Reynolds number that we tested. So what this tells us is that for every Reynolds number, we have an optimal dimple depth ratio that minimizes the drag. And if you deviate away from it, either to the left or right, it's detrimental to the drag. Yes.
The C prime B RMS, is that the fluctuation?
Yeah, so that's what I was about to say
Oh.
next. So what's interesting we find was, although when we increase the dimple depth ratio, we increase the drag coefficient, but when we look at the RMS of the drag fluctuations, they remain constant. So that's what we think was quite interesting. But now we have systematic variation of drag as a function of K by D. And now we can think about how to correlate that with the near wave measurement. So again, to remind you, we're looking in a 2D plane, equatorial plane passing through the center of the sphere. And what we are looking at is the time average vorticity contours. And they are overlaid with time average streamlines. And we're looking at drag coefficient, we're looking at Reynolds number of 90,000. So initially we see that for dimple depth ratio 0 or 0.002, there's not much difference in the flow separation location. And if we look at the correlated drag coefficient, there's not much difference in the drag coefficient. But when you go to K by D of 0.003 and 0.003, you can visibly see the delay in flow separation. And that is correlated with a rapid drop in drag coefficient. And then from these PIV, we can also estimate the separation location. And then we see that the rapid drop in the drag coefficient was associated with rapid rise in the separation location. So separation location is measured from the front stagnation point to that. So as the separation angle increases, you're saying that there's a delay in flow separation. And when we increase K by D, we see that in the drag and also in the flow separation angles, there's not much difference. And if you continue to increase, so I don't have the data here, but in the next version, morphable version 2.0, I will show that data. We see that the flow separation location starts moving upstream. And that is correlated with the increase in drag. So to show you a video of that, so that you can see in real time the delay in flow separation. So you would be able to see when the dimples are actuated here. And we're looking at instantaneous stream velocity. Again, at Reynolds number of 90,000 and K by D 0, 0.002, we don't see much change. And boom, when we have K by D of 0.003, we see the delay in flow separation. And then if you increase it further in the instantaneous streamline velocity, you do see the signatures where it starts to move upstream.
So here, you keep the flow speed the same, run it with some initial height. And then
Height.
the dimple height, then you change it
So we started off with smooth.
and then stop. Okay.
Yeah, so the wind speed is constant, which is that Reynolds number of 90,000. And then we started off with smooth configuration. That's what you saw, K by D 0. And then we changed the dimple depth
And
in
with
real
each
time.
step, you let it run with
Yes.
some sort of statistically steady.
Yeah, so here we programmed it. We didn't let it run for more than a couple of minutes, just a couple of seconds. And then we changed the next dimple depth. Okay, so now we see that we have a morphable sphere version 1.0 that gives us an ability to precisely control dimple depth on demand. And then we systematically studied the dimple depth ratio and how it affects drag. So now the question is, can we figure out a predictive model for optimal K by D as a function of Reynolds number that would minimize drag coefficient for the entire range of Reynolds number? So following Che et al. In 2019, so this is an empirical model based on a logistical function here, which basically can be fitted into all the prior literature work on smooth sphere drag data. So what it tells you is a CD as a function of Reynolds number, and any Reynolds number is a function of the subcritical drag coefficient, which is mostly constant in the subcritical range. Delta CD is the difference between the subcritical and postcritical drag coefficient. W is the width of the transition, and REC is the critical Reynolds number. So you can fit this onto smooth sphere drag coefficient, and then we extract the subcritical Reynolds number, subcritical drag coefficient. And we see that it came around 0.55, and then we also recover the right critical Reynolds number in our case. And now we can fit this parameterized logistical function onto all the data sets that we had at varying K by Ds. And that's what you're seeing here. And these models, they match pretty well with the measured data with the R-square values of more than 0.9. And in fact, the systematic variation of dimple depth ratio, the figure that I showed, the curves were actually the model. And then we can extract how the delta CD and the critical Reynolds number would vary as a function of K by D. And now we can identify this optimal curve highlighted in red, which represents the optimal dimple depth ratio as a function of Reynolds number to minimize the drag. So this is the proof of concept for the closed loop control. And then you will see that in the version 2.0 that I will talk about later, we improve on this one. So we're looking at time trace of drag coefficient, and these are the instantaneous values. And in red, we're looking at moving average over a window of 1 second. So these three figures are three different Reynolds number. We have 55,000. The second column is 90,000, and this is 120,000. And then the green regions are where the morphable sphere actuates a certain dimple depth. So we start off with smooth configuration for a minute. So you see that we are hovering around 0.55 drag coefficient. It stays constant. And now, ideally, once you have that optical model of optimal k/d as a function of Reynolds number, all you really need is a velocity estimation, right? So you can just stick a pitot tube in your setup, right? Where when the velocity change, you know what the velocity is. And using that control model, you can actuate the optimal dimple depth. So for this demonstration, we thought, let's just use the sensor we already have, which is the force sensor. So we didn't put an extra velocity sensor in this case. So what we do is we measure the drag coefficient at smooth configuration, and we start off with 0.55, and that gives you an estimate of what's the Reynolds number. And then the morphable sphere actuates the optimal k/d using the control model. And then we see that it has actuated that k/d, and then the drag reduces. And then we tried that at different Reynolds number. In this case, in one set, we're not changing the Reynolds number. And I will show that in the following slides, where in one set, we change the velocity. And then the protocol that we follow is, again, come back to smooth configuration. And then with the force measurement, you estimate what the Reynolds number is, and then use the control model to actuate optimal dimple depth for that Reynolds number. Yes.
Here, how do you know what k/d to do at a certain Reynolds number?
So that, yeah. So the question was, how do you know what optimal k/d is for a certain Reynolds number, right?
In this implementation?
Yes.
Yeah.
That comes from this model that we programmed in Arduino, right? So for this, we need to know what's the Reynolds number.
I see. So you performed the experiments for different values of the roughness, from which you extracted the optimal value. Is that right?
Are you
Then-
talking about this predictive model? Yes.
Yeah, right.
Yes.
Then you're using this optimal value as information for the control loop implementation.
Yes,
for the
yes.
same. Okay.
So the systematic study that we did, we have identified the optimal k/d as a function of Reynolds number to minimize drag. So this is the control model that you need to implement closed loop control. So from here, the flow control community can take over. They can stick a pitot tube. Whenever there's a velocity change, they will know from pitot tube what the velocity is and what the Reynolds number is. And they can program this control model in their closed loop approach, and they would know what k/d to actuate. And then because this approach is validated, we know for every k/d what depressurization levels we need. So the morphable sphere would actuate that particular k/d. So to summarize what we have learned so far, that we developed a smart morphing strategy here that allowed us to adaptively change dimple depth with changing flow velocity and also on demand. And we used that to systematically study the effect of dimple depth ratio. And we found that as you increase dimple depth ratio, the critical Reynolds number where you see drag crisis decreases, but the drag coefficient or the minimum drag coefficient achievable in post-critical regime actually increases. And then we used that data to develop a predictive model to relate optimal k/d as a function of Reynolds number to minimize drag, and then use that model in a very proof of concept closed loop control approach over a sphere. So here I've just scratched the surface. So this paper is under review, and you can look up the archive for more details. So at this stage, we have a toy model at hand, and the team was very excited. What else can we do with it? So the one question that came to our mind was, can we generate lift using this morphing strategy? So in order to start that, I will first ask you, audience, so have you seen instances around you where you see lift being generated on a spherical body?
Yes.
Yes,
Yes,
yes. What are those?
Like the insects, when they're flapping their wings, and the bird, they change the shape of the morph their wings, so they generate the lift on the vortex.
Yeah, so that's a good mechanism of generating lift for that specific shape. I'm asking about a spherical body.
Yes. Yesterday,
Uh-huh.
In the game, Tigers game, there was a curveball.
That's what I was getting at. Curveball in soccer, right? So we see that in sports all the time, where you impart rotation on a soccer ball in this case, and it dramatically changes trajectory, which is known as curveball in soccer. So this is known as Magnus Effect, right? And another very cool example of Magnus Effect. So this video, I took it from the YouTube channel Veritasium. That's really good science YouTube channel, by the way. And what we're looking at is basketball thrown from Gordon Dam in Tasmania, Australia. So this gentleman has a basketball and he drops it into the dam, into the river. And then you see that it pretty much goes straight down with the wind. It sways here and there. And now see what happens when he gives just a little bit of backspin. It goes all the way into the river, just with a little bit of backspin.
Did he go down and get it out?
I guess no. So what's happening over here? So in order to look at that, I'm going to show you dive visualization videos. This is from an earlier video in water tunnel. And we're looking at dye visualization at a Reynolds number of 5,000. So we're looking at fluorescein dye, which is illuminated using UV lamp. And alpha is a non-dimensional rotational rate. So when it's not rotating, the flow is very chaotic. It's three-dimensional, right? And now the alpha would change. And it's moving in clockwise direction. So you see that the wake is deflected downwards. And when you further increase the non-dimensional rotation ratio, the wake deflects even further down. So here we see that as we impose rotation, the wake deflects downwards. So we have an equal and opposite force in the other direction. And that is Magnus Effect. And that's what you see in curveball and also in cricket. So in all these instances, we are creating lift by imparting rotation, right? Now, what we are thinking about is, can we generate lift just by changing the surface texture or topology, right? And again, we see that in sports. So many cricket fans here? Okay, there are a few. So this is how a professional cricket ball looks like, and then you see it has a seam. So as it turns out in cricket as well, swing, which is another word for Magnus Effect, is generated just by this asymmetric seam. So the optimal configuration here is, this is from Deshpande et al., published in JFM, is around 10 to 30 degrees. Then what happens is the boundary layer that develops at the top surface because of the seam, just like the dimples, it transitions into turbulent boundary layer and we have delay in separation. On the smooth side, where we don't have seam, we have laminar separation. So the wake is deflected this way. So this is the direction of conventional swing. And interestingly, if you have very high Reynolds number, you can also see inverse Magnus Effect or reverse swing in cricket, where now on the smooth side, the boundary layer transitions to turbulent, and then there's a delay in separation. And on the top side, we are in the post-critical regime, boundary layer gets thicker, and it starts moving upstream. And now the wake is deflected in the opposite direction from what is predicted with Magnus Effect, and you have reverse swing, right? So we saw that specifically in realm of sports, people have looked at how this asymmetric seam would be able to generate Magnus Effect. So in a sense, what we need for lift is asymmetric boundary layer separation, right? And that leads us to the question, can we generate lift on a sphere solely due to asymmetric roughness on its two sides? And if yes, I mean, the studies on the cricket ball suggest we can, right? What's the maximum lift that you can produce? And how does that lift correlate with the roughness parameter? And how that lift will vary with the Reynolds number. And just like the previous study, do we have an optimal roughness parameter that optimizes lift or maximizes lift for a wide range of Reynolds number? And here comes Smart Morphable Sphere version 2.0. So this version of the Smart Morphable Sphere, so thanks Fernanda for this nice gift. So what we have in the skeleton, half of the skeleton has holes and half is rigid. And just like the previous time, we cover it with a thin latex sheet, and we can control precisely the dimple depth. The only difference is that we are making it rough only on one side, while the other side remains smooth. So this is very similar to that of the asymmetric seam that you see in cricket. And here again, the dimple diameter ratio and the coverage ratio is matched with, not the coverage ratio, the dimple diameter ratio is matched with professional golf sport. And then we can calibrate it again, just like the last time. And by precisely controlling the pump activation time, we can change the dimple depth. And then we're looking at 3 different instances. This is when you have higher dimple depth, where the activation time is larger. And just like the last time, we have a precision of 0.01 millimeters in this case. And thanks to aerospace engineering department again, we got access again of the open circuit 2x2 low speed wind tunnel. The Reynolds number varies from 60,000 to 130,000, and K by D we varied from 0 to 0.01 in increments of 0.001. And we are doing simultaneous force measurement using ADI Mini 40, which has a resolution of 0.01 newtons in both X and Y axes, and near wake measurements in equatorial plane using 2D PIV. So now let's look at what happens when we systematically vary the dimple depth. So starting off with K by D of 0, which are these symbols here. So you see that we don't generate any lift. Although at higher Reynolds number greater than 100,000, we do see slight generation of lift. And that is because in version 2.0, so for all these morphable sphere, we pre-stretch that latex sheet so that we don't see any flutter in wind tunnel. And as a consequence, we do have small indentions, which is not significant, but at very high Reynolds number can generate a little bit of lift. But if you compare it with the lift that we can generate with optimal K by D, it's totally insignificant. So now, as we increase the dimple depth ratio in this case, in the direction of arrow, we see that we start generating lift. So let's look at this cyan symbol, which is 0.002. So the critical Reynolds number is when the lift starts generating. And then we see that it monotonically increases with Reynolds number, and then it plateaus. And as we increase the dimple depth ratio, the critical Reynolds number at which we start seeing that generation of lift decreases, right? And also the maximum, the post-critical lift in this case, in fact, decreases as we increase the dimple depth ratio. And one thing to note here is that, so I'm referring again, Choi et al. And Juha Kim et al., which looked at Magnus Effect and inverse Magnus Effect that was published in JFM 2014. The lift coefficient that you can generate with imposed rotation is around 0.4. And here we see that we generate lift as much as that produced with rotation. So that was pretty interesting for us. So again, if we fix the Reynolds number and we vary K by D, so let's look at this 70,000 here. We see that in the beginning, for a fixed Reynolds number, we increase K by D, nothing much happens. And then we have sudden sharp rise in the lift coefficient that we generate, and we can monotonically increase the lift coefficient. And then we reach an optimal value where the lift is maximized. But if we continue to decrease, continue to increase the dimple depth ratio, we see that the lift coefficient starts decreasing. And then if we increase the Reynolds number, let's say to 100,000, red symbols here, now we start generating lift at a much lower dimple depth ratio, and we reach much higher lift coefficients. But again, if you increase K by D, you start decreasing the lift that is being generated. And in order to correlate the forces with the Nair-Wake measurements, now we are again looking at 2D PIV measurements in the equatorial plane. So we're looking at time average time average vorticity fields overlaid with time averaged streamlines. And for this Reynolds number, I will put this to the side. The correlated lift coefficient as a function of K by D is also given. So we see that for 70,000 Reynolds number, initially we don't see much happening in the Nair-Wake measurement. But when you go to that optimal K by D, which is highlighted with that shaded region, we see that you can clearly see the delay in flow separation on the rough side, and that leads to wake deflection, and that is associated with the maximum lift for that Reynolds number. And if you further increase K by D, the lift starts decreasing, and you can see here the flow separation location starts moving upstream. And then similarly, if we look for much higher Reynolds number now, the same effect happens at much earlier dimple depth ratio. And the highlighted K by D is where we start seeing the maximum wake deflection and maximum lift generation. And if you further increase K by D, you start losing that lift. And just like the last time, we can estimate the flow separation location from PIV images. And here, because one side is rough, one side is smooth, we actually look at delta theta S, which is the difference between flow separation location at the rough side minus what's there at the smooth side. So larger the difference, larger the wake deflection. So we see that the lift coefficient and this delta theta S, the difference in separation angles, are correlated. When the difference increases, we see increase in lift coefficient. And then when the difference in separation angle decreases, we start seeing the loss of lift. And now, just like the last time, we can fit an empirical model, parameterized logistical function here. We can extract how the critical Reynolds number and the maximum K by D varies as a function of K by D. And then if you normalize Reynolds number with the critical Reynolds number and lift with the maximum lift, then we see that we collapse all the data onto a single curve. And we can also extract, I'm not going into details because I've already explained that in the previous slides. We can extract optimal K by D here again, but this time that optimal K by D is to maximize lift. And that is shown in this red highlighted curve. And now we do a much better job at this time, looking at time trace of CL and the associated Reynolds number. And in the same set, we are toggling the wind speed in our wind tunnel. So we start off with smooth configuration. We measure the lift. We see that we don't generate any lift, right? And this is where the dimples actuate for that Reynolds number. From the control model, Arduino knows what the K by D needs to be actuated, and we have the calibration, and those dimple depths are actuated, and we maximize lift. And now the shaded purple region is where we toggle the wind speed. And this is where we reduce the Reynolds number, we reduce the flow speed. And then what happens is when the algorithm, this is how we programmed it, when the algorithm detects change in velocity, it releases the dimple to come back to smooth configuration. And that is what you're seeing here. The lift starts dropping and it goes to 0 again because the morphable sphere has come back to the smooth configuration. And in smooth configuration, we know what the drag coefficient should be. So we get an estimate of what the Reynolds number is. And as soon as the smart morphable sphere knows what that Reynolds number is, from the control model, it can actuate that optimal dimple depth and maximize the lift again. And then here, we toggle the wind speed again. We again reduce it. And then it goes back to smooth configuration to gauge what the Reynolds number is. And then actuates the optimal K by D to maximize lift. So in this figure, what we're looking at is a closed loop control approach, where we change the flow velocity and the morphable sphere comes back to maximize lift. So it doesn't matter what the flow velocity is, it will always maximize the lift. So to summarize what we did in Smart Morphable Sphere version 2.0, so we saw that by asymmetric roughness, we can generate lift comparable to that produced by imposed rotation, which in our opinion is a big thing. And you generate lift forces as much as 80% of the drag force. And we also found that the optimal dimple depth ratio varies with the Reynolds number. So you need deeper dimples at lower Reynolds number and shallower dimples at higher Reynolds number. And then here we leverage the asymmetric boundary layer separation on the two sides of the sphere to generate lift. And we saw that the flow separation on the dimpled hemisphere is delayed, while the smooth hemisphere remains unaffected. And that led to wake deflection, leading to lift generation. So this set of study sets the foundation for applications in maneuvering for underwater and aerial vehicle. And again, I have just scratched the surface. This paper is again under review, but it's on archive. So feel free to look at the archive journal if you're more interested. So that was good. But remember, we have this Smart Morphable Sphere version 2.0. We are very happy about it. And now we're thinking about maneuvering, right? So imagine you have an underwater vehicle you would like to maneuver. One limitation with what we just did is that you're generating lift only in the direction of roughness, right? What if you want to go right, right? So of course, for that, you need that ability to be able to independently control the two sides of the sphere, so that if you want to go left, you actuate this side and you go left. You want to go right, actuate this side and you go right. And you can precisely control the lift being generated. If you want to maximize lift, you can do that. And that's where the Smart Morphable version 3.0 comes. And this is the ongoing work. We're still drafting it up, so I will not spill a lot of details here. But in this version of the Smart Morphable Sphere, we are able to independently control the two sides. And in order to demonstrate that we can generate lift on either side, we actually gave a switching frequency. So now we're looking at time trace of lift coefficient as a function of time. So we switch on one side, we generate lift, we go back, switch the other side, and you see this variation in lift coefficient. And then we also have this smoke visualization that we did wind tunnel. You actuate this side, you let it start again. So the wake now seems deflected upwards and the dimples were actuated on this side. And then you will see it turn in the other direction when the dimple depths are actuated on the other side. So with this version, we can achieve wake deflection on both sides. And this is currently what we're working on. So this was very interesting. With this version 3.0, now what we can do is not only can we generate lift, we can generate lift on either side, and we can also actuate both the sides simultaneously to reduce drag, right? So now imagine an underwater vehicle, right, that can maneuver without any protruding appendages, while also avoiding flow separation at high angles of attack. ONR be like, now we are talking. So this is the image that I produced using DAL E3, and it just wouldn't take the prompt of no appendages. But so this is the futuristic picture where you wouldn't need any protruding appendages to maneuver, and you can just use change the surface topology to do that. And then when you have high angle of attack, you have massive flow separation, which is very detrimental. You actuate roughness and you reduce the flow separation on demand. And if you're fans of Star Wars, which my postdoc and the students were, they like to claim that with version 3.0, they actually developed the original Death Star. So we're always looking next. So in the interest of time, just where we are heading in the lab. So we're now thinking about looking at how we can leverage this smart morphing strategy in other applications. And we're looking into bio-inspired underwater propulsion, how fish propels in water. So we have a flapping foil. And one of the questions are, can we improve propulsion efficiency of a flapping foil for varying parameters using smart morphable skin? And we have new postdoc on board, Lokesh, and undergrad Amy, and they both are supported by Center of Naval Research and Education at UM. And to piece everything together, we are working on fundamental fluid dynamics on bluff bodies as well as in foils. And in terms of methodology, we're looking at how can we manipulate flow around these bodies to achieve a certain goal. And we have looked at active closed loop, we've looked at passive boundary effects, and we are also very interested in adaptive passive flow control. And in terms of application, we are really interested in renewable energy harvesting and enhancing hydrodynamic or aerodynamic performance of unmanned aerial or hydrodynamic vehicles. So with that, we'll have a lot of exciting projects coming up in the following winter semester when we finally have the water tunnel installed. And feel free to get in touch, and we will be hiring students. So with that, I will conclude my talk, and I will take any questions you have.
Any questions?
So, Professor, I have two questions. In leading to the first question, can we go back to the slide where you showed the shark skin?
Shark skin in the beginning?
Yeah.
This one?
Yes. So there is like underneath the rivulets when they left, there is a little green vortex. Is that a vortex that creates suction?
Yeah, so that's what they reported in their study as well, that what is that mechanism? So it's similar to flaps, so to speak, where they lift up and the flow reattaches again. And they see that they form these cavities when these micro scale structures lift up. And that's the probable.
There's a vortex.
Yes.
So if we zoomed in on the dimples, do we expect to see the same structure in there? Is the flow doing the same? Do we have like a secondary vortex that's sucking the flow back in?
Yeah, so I will repeat the question for online viewers. So the question is, when we have these dimples, do we expect the similar kind of flow separation, local flow separation in the dimples?
Yeah, mainly a vortex in that region.
Yeah, so there was a study by Bratlis et al. They did CFD simulations and they really zoomed in and looked at what's going on at the dimple depth. We can't do that experimentally with that precision. So what they found was that the flow indeed locally separates within these dimples. And in fact, if you are at post-critical regime, that is detrimental for drag. And the main mechanism here is that you have increased wall momentum that brings the higher momentum fluid back into the boundary layer and energizes the boundary layer. And then you have this turbulent boundary layer that delays the flow separation.
So when you non-dimensionalized K over D, D was the diameter of the hole itself or the big sphere?
Yeah, so the K by D that we used, D was the diameter of the sphere.
So sorry, I'll just ask.
We can also
Yeah,
chat.
Yeah,
Okay.
yes. There's a question from the back.
Yeah, I think my question was related. I was just wondering, what is the fundamental physical theory explaining how the depths affect the detachment point or the boundary layer detachment on the sphere?
Are you talking in context of dimples?
Yes.
Okay, so the question is, what's the physical mechanism, how there is a delay in separation when you have dimples?
Yeah.
So I kind of highlighted that when I was responding to Mohammed. So what has been shown is that when you have these dimples, they generate these streamwise vorticity. And what they're doing is they're bringing the high momentum fluid towards the boundary layer close to the wall. So now you have energized boundary layer. And that when you have laminar separation, because of shear layer instability, it comes back and reattaches with the spherical surface, but quite downstream. And then in the end, you have turbulent separation. So that in effect, you see there's a significant delay in flow separation. So that's in a nutshell, I would say.
But then are there theories to explain what is the reason for particular critical depths versus the Reynolds number effect? Are they looking at additional instability mode excited by these dimples, vortic structures in relation to their frequency?
Could you rephrase your question again?
Yeah, so I was wondering, like, what's the next explanation in explaining the trend we observed when we go a larger Reynolds number, we see a different critical depth ratio. What is the how does that picture fit into the current physical?
So if I understood correctly, what you're asking is that insight that we found that the critical K by D is changing with Reynolds number, right? So how do you physically explain that, right? So again, I would go back to Breathless et al., where they looked at CFD simulations very close to the spherical surface. And what they found was that as you increase the K by D, the dimple depth ratio, you're energizing the boundary layer more and more. And then you have this turbulent boundary layer separation. But beyond the critical K by D, now you have flow locally separated within the dimple, and you have local pressure penalty that in post-critical regime, now you have frictional drag dominant as well. Boundary layer is very thick, and it increases the frictional drag in that regime. So depending on K by D, we may have different mechanism at play at different Reynolds number, if that answers your question.
So for the drag and the lift, when you try to control the maximum lift, for example, how do you know like the dimple ratio to the maximum lift? Is that the limitation of the depth of the dimple, or is like some reference command you would like the this mechanism to go to reach to that specific lift you want?
If I understood your question correctly, are you asking that how do we know that we achieve that optimal K by D?
Yeah, like the maximum lift, how do you know like now this is the maximum lift you generated? Is that like you command give a reference to control the K by D, or is like the limitation of like you can reach it to at that specific Reynolds?
Okay, so what the algorithm is doing, so with the control model, we just know for this Reynolds number, this is the optimal K by D to maximize lift. And all the algorithm is doing is as soon as it knows, has an estimation of Reynolds number, it just actuates that dimple depth. And the way we know is we are looking at the lift, and we see that it goes back to the maximum lift coefficient, which is 0.4. So from there, we know that it has achieved maximum lift.
So the maximum lift is like a reference you have known.
Yes. And before that, as you saw, that in order to get the control model, we systematically varied dimple depth ratio. So from there, we already know.
Thank you.
I know you mentioned the sphere version 3. I'm a little curious about the experimental setup and what variables you can test at the same time, because now theoretically you have new combinations of parameters and multi things that you can optimize. Like say if you're trying to have, you can change dimple depth on one side and the other to create lift in one direction or the other, and then also a ratio between the two sides to find the optimal like minimize drag in relation to lift. So I'm just wondering how that's set up, and I guess testing matrix
Would
be
look like.
how you wrap your head around that.
Yeah. So if, again, I will rephrase the question for online viewers. So what you're asking is for the smart morphable version 3.0, what are the parameter space we're looking at, right? So what we're looking at is, so if you want to minimize drag, you don't need different dimple depth. If you have dimple depth, you will generate lift. You want the optimal K by D across the entire surface area that would minimize the rear wake to give you minimum pressure drag. When you want to generate lift, that's when you want asymmetric roughness on two sides. And what we looked at already is that we can maximize lift. And because we already have all the data we can precisely control lift. I mean, in case you don't want to maximize lift, for example, you can precisely control. One thing we could do is we can set a switching frequency. And then that's where things starts getting complicated. And we have a new student on board who would, I see you talking to him. So what we can do is we can implement different switching frequencies. And that way we are introducing new frequency into the system. And let's say you're talking in context of flow-induced vibration, which is again, a big thrust in our lab, then how would that affect? We can, in a sense, use this to enhance those vibration if we are extracting renewable energy, or if we are suppressing vibrations for offshore structures, we can minimize it. So to summarize what you asked, in terms of parameters for minimizing drag, we've already looked into it. And we need constant optimal dimple depth across the entire surface. And for lift, we've already looked into it in version 2.0. What's the optimal K by D is to maximize lift. And we can now have different frequency. That's the additional frequency that we can introduce into the system. If that answers completely what you were asking. Okay.
Go ahead.
Yes.
I was just curious, and you see, for your relations for K by D as a function of Reynolds number for both lift and drag, did you see any convergence between the two equations, or is a similar K by D that maximizes lift, so would minimize drag?
Yeah, that's a very, very good question. So to rephrase what you've asked, you're asking is when you're generating lift, the optimal K by D that gives you maximum lift, is that related to optimal K by D when you're trying to reduce drag? And I would say the answer is yes, right? So if you think about these two in isolated fashion, you have dimple sphere and your smooth sphere. So the K by D that would maximize the lift is where you would have the maximum delay in flow separation. And if you have the same dimple depth across the entire surface, that's the one that would give you minimum drag, right? So they are related indeed. That brings me to the limitation of this. Here we considered the two hemispheres as isolated systems. But if you look at the intersection of the two, there's really intriguing three-dimensional effects that are happening that we could not address with the current experimental setup that we had. Yes.
So in your application, you mentioned maneuverability of underwater vehicle.
Uh-huh.
Do you think there'll be changes because of the pressure of water and at different depth? So will you be, I guess, changing the fluid inside or changing the skin, or how do you?
Fluid inside. Okay, so this works on pneumatic actuation. So your question is specifically to the hydrostatic pressure when you go in depth, let's say you have a submarine.
Can I answer that question?
Yes.
The density, that outside it's now 1,000 times denser.
Yeah, so that's a very good question. So we tested in air. So in a sense, I would conjecture that if your outside pressure is higher, if you still have a good pneumatic actuation system, you can compensate for that, right? If you have prior knowledge of what's the pressure outside, you would still be able to go to that optimal dimple depth that would minimize, let's say, drag. Right? It's pneumatic actuation. As long as you have that information, I think it should be able to do that.
Can I ask a-
Yes.
So follow up to that, it might be interesting to look at the energetics of it. Right? There's a certain energy being put into activating, getting this optimal geometry, and certain energy being saved by the drag reduction, and that would depend upon the density ratio. That was just a thought I had from controlling. The other thought was the scaling K by D. I mean, typically when one looks at, it might be interesting to look at scaling it with the boundary layer thickness, because when one looks at roughness effects or trip effects, typically it's K plus, and so that's why at low RE, a big thing works, right? At high RE, it's too thick.
Yeah.
That's a classical thing when we trip things. So it'd be interesting to just look at the data in terms of K by delta, I think, globally, or K plus effectively, to see the Reynolds number is collapsed by that behavior.
Yeah, that's a very interesting idea, and then we'll look into that.
rest of that.
Yeah.
Okay, we are about 10 minutes, but this was great. Thank you so much, and thank you all for participating.